Hello, students. Good evening. Welcome to another class of Vedantu Karnataka. This is Catherine, your physics master teacher. Students, quickly, can you let me know if I'm audible, visible, and if I'm live as well? So let me also check. Yes, I can see myself. Good evening. Welcome to another class. Yes. Hello, Praveen. Hello, Harshita. Hello, Adarsha. Hello, Balraj. Okay. So, how are you all doing? Hi, RXBTCC. Are you all doing well? Yeah. How's your PU classes going? How's your KCT preparations going? Students, if you're all looking for offline classes to prepare for your KCT, your NEET, or JEE, or even if you're an 8th standard student, we've got you covered. Okay, you can come to our Vedantu offline center, which is in JP Nagar. You have the best teachers there. Okay, and if you want to learn online, you have us. Yes. So we'll just wait for one more minute and then we can start our lesson. So, wait a minute. Yeah. I'm doing good, RXBTCC. I hope you're also doing well. Praveen's doing well. Okay. So as you've seen the thumbnail and you those who have been following my classes, today we're going to look at dipoles. Okay. So let's look at dipoles. So what all did we already see? We already looked at Coulomb's law. We looked at electric field. We looked at electric potential. We looked at potential energy. All of that. Now today we'll be dealing with dipoles and torques. Are you all ready for today's lesson? If you're ready for the class, can you quickly put some fire emojis in the chat? Yes, quickly some fire emojis in the chat. Okay, now let's start. So, what is an electric dipole? And then what are these polarities and what are all those things? So, an electric dipole is when you have two charges. Okay, so you need two charges, positive charge and a negative charge. Okay, so to make a dipole, you always need two charges which are opposite. They should have the same magnitude, but they should be opposite. So you should have a positive charge, negative charge, and they should be separated by some distance. Okay, so we can say let the distance be L. Now this is a dipole. This is a dipole because it has two equal charges which are opposite and it is separated by a distance L. Alright. So a dipole means you have two equal and opposite charges separated by a small distance. It's a very simple concept. Okay. Now if you want to have a more precise definition, I have that as well. It is a pair of equal and opposite charges, so say plus q and minus q, separated by a small distance. Okay, now I can give you some examples of dipole. You might be thinking, where are these dipoles used? For example, the HCl molecule. Okay, so for HCl, what happens? You have hydrogen and then you have chlorine. Okay, can you see? Yeah, you have hydrogen and then you have chlorine. Okay, so chlorine is negative, hydrogen is positive, and they form a bond. They are separated by a distance, so this is a dipole. Now, if you look at H2O, okay, so if you look at H2O, you have hydrogen, you have oxygen, you have another hydrogen. Okay, so each hydrogen is positive, each oxygen is negative. So you can see there are two pairs of dipoles here. This is one dipole, this positive hydrogen, negative oxygen. This is another dipole. Both are separated by a distance. Okay. So for a dipole, it has to have two polarities. What is polarity? The charge. So what are the two polarities in a dipole? One should be positive, one should be negative. So you can see HCl and H2O, they both behave as dipoles. Okay? Yes, RXBTC. Hi, Savio. Okay. So, yeah, let's move on. Now, let's look at the electric potential of a dipole. So you can see if you have a dipole, for example, if you have a positive and a negative charge. So this is a positive, let's use some color. This is a positive charge, and then let's take black. This is a negative charge. Okay, so both of these together make a dipole, and to make this dipole, when I say to make this dipole, to bring these two charges together, we've already learned in our previous classes, if you have a positive charge, field lines always move out of the charge. Isn't it? Do you remember? Those who have not watched the class, please go watch the class. If you have a positive charge, you can see field lines always move out. Okay? Now, if you have a negative charge, field lines always move in. Yes? Positive field lines move out, negative field lines move in. So what will happen if a positive and a negative comes together? So if you have positive here, you have a negative here. From positive, field lines move out. It goes into the negative. That is what you see here. You see all these field lines, they go from positive to the negative. Okay? Yes? If it's the other way around, like this. Anyways, from positive to negative. Now, if you look at the equipotential lines on the dipole, yes, so electric field of a dipole is like that. It always moves from positive to negative. So this is how it will look. This is how the electric field of a dipole will look. Now, how will electric potential of a dipole be? For electric potential, you don't have to look at the field lines, but you have to look at the equipotential lines. So what are equipotential lines? That also we've discussed in the last class. So equipotential lines are lines which have the same potential throughout. I've explained it in more detail in the last class. You can go watch that video. So you can see here, if you take this line, the potential is just 0 because it's at equal distances from the positive and negative, and that particular point potential is 0. If you're going near the positive, potential becomes positive. Near the negative, potential becomes negative. So how will the field lines be? The field lines will be something like this. A straight line, and then something like this. You know, like a creature which has two eyes. It will look something like this. The green lines. Okay, the green lines represent the electric potential of a dipole. Okay, is that clear? Thank you, Atharv. Right. Thank you, Atharv. You might also be very handsome. I haven't seen you. I take your compliment. Okay. I didn't want to break the flow of what I'm explaining. So, yeah. Is this clear to all of you? So, this is how electric field lines are and electric potential is for a dipole. Okay. Next is, okay. Next is the mathematical overview of electric dipole. So, mathematically, how do you look at an electric dipole? So, theoretically, now we know you have a positive charge, you have a negative, they're separated by a distance, that forms a dipole. Now, mathematically, how you look at it is basically you look at the amount of charge, okay? You look at the separation between them and you can form a relationship. That we will look into that in the next slide. So, that mathematical relationship is actually called as the dipole moment. Okay, so what is dipole moment? Dipole moment is the strength of an electric dipole. So we know what an electric dipole is. So how strong that electric dipole is, you determine by looking at the electric dipole. Sorry, the dipole moment. And what is dipole moment? It is represented by the alphabet P. P is also a vector quantity. Vector quantity means it has a direction. Okay, so dipole moment has a direction. Now, very important thing is if you have a positive charge, you have a negative charge. This is a dipole. It is separated by a distance of L. Okay, in some books you take it as 2a also. Here I'll just take it as L. The direction of the dipole is always from negative to positive. Okay, as I said, dipole moment is a vector quantity. So the direction of dipole is always from negative to positive. Okay, that's very important, students. But you have seen that electric charge, how does an electric charge work? So if you have an electric charge, if you have positive and negative, the electric field lines always go from the positive to the negative. But a dipole always goes from negative to positive. So that is one thing you have to keep in mind. The direction, and directions are important because dipole moment is a vector quantity. What is a vector quantity? A quantity that is determined by direction and magnitude. Okay? Yes, no. So these are two important points. Okay, very important. Electric field goes from positive to negative, but dipole moment goes from negative to positive. Okay. Now, how do you get the dipole moment? Dipole moment is by taking the formula. This is the positive charge. This is the negative charge. As I said, in your NCRT, they are separated by a distance of 2a. Okay. So this is plus q. This is minus q. They are separated by a distance of 2a. And some of you might be thinking, why 2a? It's just because, to do derivations, it's easier to take 2a. Because when you take the midpoint, you can take one part as a and the other part as a. That's all. For that easiness, you take it as 2a. Even if you take it as L, it's okay. Okay. Now, the dipole moment is basically what? It's represented by the alphabet P. It is the charge into the distance between the charge. Okay, so if the charge is Q and the distance between them is L, then the dipole moment will be QL. So imagine the charge is 5 and the distance between the two charges is 10. Then the dipole moment will be 50. Okay, that's all. If you have the two charges and they are at a distance of 10 meters. If that is too much, it's very small. Okay, so 10 micrometer we'll put. Then it's 50. Okay, so that's all. So dipole moment is basically the charge into distance between the two charges. So 2a is what? The distance between q and plus q. Okay? Is that enough? Is that clear? Yes? No? So yes, this we already discussed. Is dipole moment a vector or scalar? It's clearly a vector. Why? Because it moves from the negative to positive direction. Now what is the unit? The unit is coulomb per meter. Why is it coulomb per meter? Because it is Q into L. Q is charge, which is coulomb. L is length, which is meter. So students, don't get confused. This is not centimeter. This is coulomb per meter. Centimeter will be small letter C and small letter M. This is capital letter C and capital letter M. So this is coulomb per meter. QL or Q2A, both are the same. Okay? Yes? No? Can you see what is written in the background? Should I zoom in? Okay? Are you following, students? Okay. Next is polar molecules and dipolar molecules. What are these? So before we look at what they are, let's just look at some images. Okay. So first let's consider water. So let's say water has H, O, and then H2O, right? That's water, H2O. All of us know that. Now, oxygen is a little negative and hydrogen is always positive. Okay, that is how they are. So, in chemistry, you might have learned that. So, you can see what is the direction of the dipole moment? It's always from negative to positive. Here also, it's always from negative to positive. So, how will the net dipole moment be? So, if you have two vectors like this, how will you find the resultant? You find out the central part. This is the resultant. So, this is the resultant. Okay, the resultant, or this is called net dipole moment. Okay, so what will the net dipole moment of water be? So if you look at it, since they have two equal and opposite forces, won't it be equal to, it would never be equal to 0, because there's one force here, there's one force here, the resultant is through the center. So this will always have some value of dipole moment, which is along the central part. So this kinds of molecules are called polar molecules. Now let's look at another example. Let's write it with another color. Okay. So this is a polar molecule. Now let's look at a non-polar molecule. So this polar molecules are molecules that have a permanent dipole moment. They will always have some dipole. So for non-polar molecule, what should I take? Shall I take CO2? Okay. So let's take CO2. So there's oxygen, there's carbon, there's another oxygen. So oxygen is negative. We know that. Oxygen is negative. So obviously carbon has to be positive. It is positive. That's why they're able to make a bond. So dipoles always move from negative to positive. Right? Dipoles always move from negative to positive. So this will be the direction of the dipole. Negative to positive. Okay. So what happens here? So dipoles are basically like this. So what happens? They cancel out. They cancel out. So the net dipole moment will be equal to 0. Because they're equal and opposite, they cancel out. In the other case, they were in two directions, so there is always a resultant. So a non-polar molecule is a molecule where the net dipole moment is always some value. It is never 0. And polar molecule is where it's never 0. Non-polar is where it is 0. Do you understand that? So P is 0. P is non-zero. Okay. So I have some, definition like differences, because in PU there's a very famous repeated question. What is a polar molecule? What is a dipolar molecule? So if you by heart, you might get confused. So I actually explained it to you. So a polar molecule has a net dipole moment. One part of the molecule is positive, the other is negative, and this creates a permanent electric dipole. This is what I just explained. And what is a non-polar? The electrons are equally shared. There is no net dipole moment. So net dipole, it's like a tongue twister. When I say it fast, it becomes dead danda. Okay? Net dipole moment. So the charge distribution is symmetrical, which also I explained. So there is no polarity, so there is no dipole moment. Okay? Very famous question in your PU. Difference between polar molecules and non-polar molecules. Okay. What's happening? Okay. Now let's move on to a question. Okay, let's look at a question. Question based on what we just learned. So 3 charges are placed at the vertices of an equilateral triangle of side A. So let's just draw a triangle. This is an equilateral triangle. It has a side A. Okay. So we'll just put it as small a because we're using small a throughout. So side A. The charges are plus Q, and minus 2Q. Okay, so let's put the charges. The charges are plus Q, minus 2Q, and plus Q. Okay, these are the charges. This is the question. What is the dipole moment of the system? The question is, what is the dipole moment of the system? So what I can first do is this minus 2Q, I will just write it as minus Q and minus Q, so that each of the other charges, each of the plus Qs have a dipole. Okay, so I will put it as minus Q and minus Q. Minus 2Q, I just split it into minus Q and minus Q. Now let us join it. Okay, so dipole moment is always from which direction? It's from positive to negative. So this is one dipole moment. Sorry, negative to positive, right? Yeah, negative to positive. See, you shouldn't be confused like your teacher. Sorry. Yeah, negative to positive. As long as you correct a mistake, then it's okay. You can make mistakes. Negative to positive is your dipole moment. So you can see these two have their individual dipole moment. So how will the resultant be? The resultant will be along this direction. Okay, these are the two dipoles. The resultant will be along the center. Okay, so the net dipole moment. Okay, this is the direction of the net dipole moment, and that is what we have to find out. Okay, so what is the formula for dipole moment? So dipole moment P is equal to what? Q into separation. Okay, so here what are the charges? Q, and what is the separation between the two charges? In both the cases it's A, so it's Q into A. Okay, now you might be thinking, ma'am, first you said it's Q into 2A, then you said it's Q into L. What is the actual value? The actual value is whatever the separation is, that is the value. So in this diagram, in this question, it's given that the charges are separated by a distance of A. So I put it as Q into A. Okay? Yes. All right. Now let's do the math. Okay? So the net dipole moment will be what? What I can do is it would be the dipole moment of the first one plus the second one. Okay. So I've already done it here. I'll write it here itself. So those who don't understand my handwriting can look at this one. Okay. So as I said, this is an equilateral triangle. Okay. So here, what would this angle be? Since it's an equilateral triangle, this whole angle shouldn't go out. This whole angle should actually be 60 degrees because it's an equilateral triangle. Okay, because it's an equilateral triangle, the whole angle should be 60 degrees. So we will just use basic vector addition. Okay, so you have two vectors that are at an angle 60 degree. How do I find the resultant? The resultant is basically a vector addition. P1 root of P square plus P square. Just write it here itself. So vector addition, P naught is equal to square root of, take this color. So what will the dipole moment here be? It will be P1, this will be P2. So this will be what? P1 square plus P2 square plus 2P1 P2 cos theta. Now we know the dipole moment on either sides are the same. So P1 is equal to P2. So now what will P net be? P net will be equal to square root of P1 square plus P1 square plus 2P1 P1 cos the angle is 60 degree. Now this will be equal to square root of P1 square. I mean, I can take it outside. There are so many P1 squares. So P1 square plus P1 square is 2P1 square. There's 2P1 square here as well. So 2P1 square I can take outside. Isn't it? Okay, I'll just take P1 square outside first. What remains? 1 plus 1 plus 2. Cos 60 is 1 by 2. 2 into 1 by 2. So this is equal to square root of P1 square. 1 plus 1 is 2. 2 plus 1 is 3. 2 and 2 cancel. So this is 3. So this is nothing else but P1 square root of 3. Isn't it? It's P1 square root of 3. Now what is P1? P1 is equal to Q into A. So P net will be equal to QA root 3. Yes, it would be QA into root 3. I hope this is clear to you. Okay. So what do you have? You have a triangle. Okay. A triangle with sides A. You have plus 2, 2Q plus Q plus Q. So minus Q and plus Q, the difference between them is A. So the dipole moment is P1. Same thing on the other side, and then you just use vector addition and do it. Okay, P1 root 3. Very good. Someone in Chinese has put the answer. Okay, good to see that people are solving along with me. Can I know what your name is? Because I can't read your name. It's in some language. Okay, so those who need a proper note, I have put it here. You can just quickly take a screenshot if you want to. Okay. Okay, let's move on. Is this clear? Do you have any doubts? Anything that you want me to answer? Yes. Okay, let's move on. Next is electric field of a short dipole at some general point. Okay, so let's just think about that. What should we do? First, let's learn it with a diagram. So we should have a what did I do? Yeah, we should have a scale. Okay, now let's simplify it. Okay, we should have a scale. So first thing, let's draw the axis. I'm just trying to improve my... Okay, you have a scale. You have an axis. Okay. So this is my axis. I have my x-axis and my y-axis. Some of you might be thinking, for this one line, you took so much time. Pathetic, man. Okay. Yeah, I made it even worse. Okay, fine. Anyways, now I have my axis. So this axis is called my axial direction. Okay. And this top part is called my equatorial direction. Okay. Now we're talking about dipoles. So obviously I need to have a dipole on my figure. So let me draw a dipole. First I'll draw a negative charge. And then I will draw a positive charge. Okay. So I'll draw a negative charge and positive charge. Now I have a dipole. And this dipole will have a dipole moment in which direction? Dipole moment is always in the direction from negative to positive. So this is the direction of the dipole moment P. So this is my basic figure. Okay. Negative to positive, I have a charge and then I have it moving along my dipole moment P. Okay. Okay. Now, how will the electric field lines be? The electric field lines will be from positive to negative. Oh, what happened? Yeah. So it'll be like this. like this, like this, like this. Okay, this is how the electric field lines are going to be. They're going to be from positive to negative. Now, next what I'm going to do is, I'm going to take a random point on my electric field. Okay, let's just take this point P. And I have to find out the dipole at that particular point P, or the electric field at that particular point P. So let's do that. Now from the axis, okay, from the axis, P makes an angle theta. Okay, from the axis, P makes an angle theta. Now, what about from the dipoles? Let's take blue. Okay, from the axis, P makes an angle theta. So from the dipoles, P would make this line and this line. Okay, from the negative and the positive, this is how you draw lines to P. Now, what about the electric field? So, if you look at the electric field, because of the negative, electric field lines always go into the negative. So, from P, because of P, the electric field on the negative will be in this direction. Yes, it will be in this direction. Now, because of the positive, the electric field will be in this direction. Yes. For the negative, the electric field will be in this direction. For positive, the electric field will be in the downward direction. So, the resultant will be in this direction. Okay. Negative, positive and resultant will be in that direction. Why? Because in positive, charges always move away. Field lines are away from the positive. In negative, field lines are towards the negative. Okay. This much is clear. Now, I know I should do a better diagram, but just erase the unwanted things. Yeah. Okay. Now, the electric field because of the positive will be how much? K, which is 1 by 4 pi epsilon naught. Charge is Q, the whole divided by R square. Yeah, the distance is R. Okay. This is R plus. This is R minus. Now, the electric field because of the negative charge will be KQ by R square itself. So, this will be plus, this will be minus, and then charge, you don't take the value or the sign because you're only looking at the magnitude of the charges. So, total electric field will be what? E plus E minus. Isn't it? The total electric field will be E plus E minus. Now, if you consider the length R to be very much greater than the length L, what does that mean? That means that if you have two dipoles, okay, if you have a dipole and the distance between them, let's say it is 1 micrometer, which is very small. Now, you take a point, somewhere here, such that it is at a distance of 5 centimeters from the line. So, the distance is 5 centimeters, the distance between the dipole is 1 micrometer. So, will you even consider 1 micrometer? You just ignore it just like it is. Okay? You simply ignore it. So, that is what we are going to do right now. So, if R is very much greater than L, what is L? L is the distance between the dipoles. So, if R is very much greater than L, then it's called a short dipole. Okay? What's a short dipole? If the point that you're considering is very big compared to the distance between the two dipoles. Now, yeah, this R is the distance from dipole. Distance from dipole. And what is theta? Theta is the angular position. Now, with respect to the electric field, the direction of electric field, this will make an angle alpha. Okay. So, the direction of electric field will make an angle alpha. This is alpha. Alright. Now, if you actually do the math for this, there's a lot of steps to that, but you don't need that at this stage. So, if you do the math to this, you will get E is equal to K into P 3 cos square theta plus 1. This will be square root the whole divided by R cube. Okay. So, this is the formula for electric field at any random point on the bit on the field of the charges. Any random point, if you take that as a formula. Now, direction is given by tan theta by 2. Okay. So, there is one more method to this which also I will discuss, but right now you need to know this formula. So, electric field at a random point will be given by E is equal to K into P 3 root 3 square root of 3 cos square theta plus 1 by R cube. Now, what about the angle? The angle tan alpha will be equal to tan theta by 2. Which is tan alpha, which is tan theta. Tan theta is the angle that, if this is the point P, tan theta is the angle that point P makes with the dipole axis. Now, what is the tan alpha? Tan alpha is the angle of the electric field. Okay, this is the angle of the electric field. Okay, is that clear? Okay, so this is the magnetic field at some general electric field at some general point on a short dipole. Now let's do an example using the same. So let's look at a question. Let's look at the question. A short electric dipole has a dipole moment of P. Okay, so the dipole moment is P, and this is equal to 4 into 10 raised to minus 30. Okay. Now we have to find out the electric field at a point that is 1 nanometer away from the dipole. So if I draw the diagram for this will be the dipole. Okay, this is the field line. This is a point P, and this distance is 1 nanometer. Okay, the distance is 1 nanometer. Theta is 45 degree, and dipole moment value is 4 into 10 raised to minus 3. Okay. Abhi, is that how you pronounce your name? Welcome to the class. Hello. So what is the formula? Formula is E is equal to Kp by R cube square root of 1 plus 3 cos square theta. K is 1 by 4 pi epsilon naught. So how will you do that? 9 into 10 raised to 9 into, what is P? 4 into 10 raised to minus 30 into square root of 1 plus 3 into cos 45 is 1 by root 2. So cos square 45 is 1 by 2. So this is 1 by 2. So this is square root of 2.5. So square root of 2.5 into 4 into 9. The whole divided by 1 nanocoulomb will be 1 into 10 raised to minus 9. So if you do the math, you will get 5.7 into 10 raised to 7. Now here, okay, there is a cube. There is a cube as well. Alright, so want me to do it? I will do it. So 9 into 10 raised to 9 times 4 into 10 raised to minus 30 into square root of 2.5, the whole divided by 10 raised to So whole divided by 10 raised to minus 9 cube will be minus 9 into 3, which is minus 27. Okay. So this will now be 9 fours are 36. 36 into square root of 2.5, the whole raised to 10 raised to minus 27 into 10 raised to minus 21. 9 minus 30 is 10 raised to minus 21. So this will be 3.6 into 10 raised to 7. So minus 27 and minus 21, I take it. And I make 36 into 3.6 into square root of 2.5 should be 1.58. So you will get the answer. Okay. Now, in the question, it doesn't say, but in case they ask you to find out the electric field, what will you do? If they ask you to find out the electric field, the angle, you just have to do tan theta by 2. So, tan 45 by 2. Okay. Which is tan inverse of 0.5 with the Clark's table, you can find it out. It will be 26.6. Okay. Is that clear to all of you? Yes. Okay. Now I'll give you another question. The question is, find the net dipole moment of the system. Okay. Find the net dipole moment of the system. Now, what is the system? The system has a charge of minus 2 coulombs here, another charge of plus q here, another charge of plus q here. Okay. So, this is dipole moment is always from negative to positive. So, here also it is like this. These are the two dipoles. Now, what we will do, we will just take this as minus q and minus q, so that both of them have their individual dipoles. Now, the distance I will take it as p. Okay, dipole moment, not the distance, the dipole moment I'll take it as p. Now, how will I find out the dipole moment? So, dipole moment will be the resultant which is along this direction. Yes, the dipole moment will be the resultant. So, those of you who are still wondering and didn't understand the question, I will draw it once again. So, consider 3 charges. Okay, the charges are minus 2q, plus q, and plus q. Okay, they are placed at 3 different points. This point is a comma 0. This point is 0 comma a. Okay, now the dipole moment will be from here to here, from here to here. Now, instead of this minus 2q, I will write it as minus q minus q. So, both the charges have their individual dipole moments. Now, if you want to find out the resultant dipole, you have to cut it at an angle which is equal to both. So, obviously, this angle has to be equal to 45 degree, isn't it? And what will the value be? The value P net will be using Pythagoras theorem, using resultants, it will be square root of p square plus p square, which is 2p square, which is basically p root 2. Okay. Now, what is p? P is the dipole moment. And what is the dipole moment? The charge into the separation. What is the separation? In both the cases, the separation is a. So, it will be qa into root 2. Yes. Do you agree with me? So, here what will the net dipole moment of the system be equal to? qa into root 2. Is that clear? So, this is basically p root 2. Is it clear? Can you quickly let me know in the chat, students? And if you're understanding this or not. Hi, Rahul. Okay. Okay. Let's move on to the next topic. Next is the electric field due to a dipole on the axis of a dipole. Students, these are 2 very important derivations for your PU perspective. For your KCET, you only need to know the final formula. You don't have to know the derivation. But because this is a class that is for students of KCET and second PU, I will do derivation and explanation of the formula. Okay, so this is very important. This is a very common repeated PU question. So what is the question? Find out the electric field due to a dipole on the axis of the dipole. Okay, oh, that's spelling mistake here, on the axis of the dipole. This could also be, the question could be axial dipole. It could be on the axial part of the dipole as well. So what does axial mean? It means that if this is a dipole, okay? So if this is a dipole, which means if this is minus, if this is minus q and this is plus q, okay? And this is a dipole. This is the center of the dipole. Let's just take it as O. What else do you need? You need to find out the electric field at a point on the axis of the dipole. So along the axis, I'll take a point P. I have to find out the electric field at point P. That is my question. Is the question clear to all of you? I have the violet colored dipole. I have to find out the electric field at point P. Now, I will just take this part to be L and this part to be L. Or A also I can take. What have I taken here? Okay, here I've taken A, so I'll do the same thing. So I'll take this alphabet as A. Okay, now you know why in your formula we learned dipole is Q into 2A. So that here when I do derivations like this, I can split it into A and A. Okay, that is why. Alright, so the total length is 2A. Now, let me just define the length between the midpoint, the center of the dipole, to point P. Let's just assume it's X. Okay. So I have to find out in the question itself, I have to find out the value of electric field at a point which is at a distance X from the center of a dipole. Okay. So that is X. Okay. Now let me consider the electric field that's acting on point P. So because of the charge minus Q, it will have a field at point P. Okay. For a negative charge, if you have a negative charge, so I say, okay, if you have a negative charge, field lines always move in, isn't it? We've learned that. So obviously from point P also, because it's a negative charge, field lines should be in this direction. Okay, so E1 is because of negative charge, this is 1, this is 2. E1 is because of negative charge, it is in log minus Q. Now from plus Q, the field lines always move away. So this has to be equal to E2. E2 will be in the opposite direction. So at point P, it experiences a force because of charge 1 and charge 2. Because of charge 1, it will be along this direction since it's negative. Because of charge 2, it will be opposite because it's positive. Okay. Now you can also see E1 and E2 are arrows of different sizes. Why? Because plus Q is more closer to P. So it will have more effect. Minus Q is very far away from P. So it will have lesser effect. So that is why E2 is longer because E2 is more closer to P. Is this much clear? Okay. Now let's erase everything unwanted and let's neatly do the derivation. Okay. First thing. E1. What is E1? E1 is the electric field at point P because of charge minus Q. So that should be equal to K into Q, the whole divided by. What should the distance be? From minus Q all the way till P, it should be minus Q till P. So, shouldn't it be X minus A? No, X plus A. X plus A. X plus A, the whole square. Alright. So, from point P till the center is X. Now, from center to minus Q is A. So, from minus Q all the way till P, till the center is X, the rest is A. So, the full length is going to be equal to X plus A, the whole square. No doubt about that? Okay. Now, E2 will also be equal to kq the whole divided by. So E2 is from where? From plus q to point P. So from plus q to point P, it is not x, but it is x minus the rest, which is A. So it's going to be x minus A, isn't it? So this is O, this is point P, this is plus q. Okay. So this whole thing is x, this whole thing is A. So I have to find out this part. So this part is going to be x minus A. Okay. So those who want to take a screenshot of this can take it and check how this is happening. Okay, let's erase that. Hi, Uday. Welcome to the class. Oh, hi, Singer Techie. Hello, Sunita Lokesh. Hello, Uday. Hi. Okay, Rahul. I already said hi to Rahul. Okay. So is this much clear to all of you? Okay, where's my square? I should put square also. Okay, so this is KQ. X minus A, so whole square. Okay, let me see if I've done the same thing here so you are not confused. E of minus Q is X plus A. Yes, same thing. Okay, so here this is E2 and this is E1. So for those who are referring this thing, okay, I'm just writing it in a similar way. E2 and E1. Okay, yeah, now let's just do it here. Let's just continue. What is the next step? The next step is to find out E net. Okay, so E net is what? Which is bigger? Obviously, E2 is bigger because E2 is from plus Q, which is more close to point P. So I will take it as E2 minus E1. Alright, E net is equal to E2 minus E1. So let's do the math. KQ X minus A the whole square first. X minus A the whole square minus KQ X plus A the whole square. Alright. So this is going to be equal to K into Q. I take it outside. Now I will cross multiply. X plus A the whole square minus X minus A the whole square, the whole divided by X minus A square into X plus A square. Okay? This is what it is. Now we can do the math. Let me do the math. So this is going to be equal to KQ. I will open the bracket. X square plus A square plus 2XA minus X square plus A square minus 2XA. Okay? Divided by A minus B into A plus B. This will be X square minus L square the whole square. Alright. So now this is going to be equal to, okay, I can here itself, I can, remove this bracket and put all the negative signs. I can multiply it with the negative sign. So this will be minus X square. This will be minus X square minus A square plus 2XA. Okay? I just put the minus sign inside. So now this becomes what? KQ, X square minus X square will cancel. A square minus A square will cancel. 4XA whole divided by KQ 4XA the whole divided by X square minus L square square, which is equal to 4XA. I will just split it so that I can, get into favorable terms for me. So this becomes 2K. I will write it as Q into 2A. Okay. Q into 2A into X the whole divided by X square minus L square the whole square. So what is Q2A? It's P. So 2K P x the whole divided by x square minus L square the whole square. Okay. So what is, this is the basic equation for an electric dipole on an axial plane. Now, the next part is if, okay, if x is very, very, very greater than a, okay, which means the distance between the dipole is very small. Then what happens? Then the dipole moment will be 2kpx the whole divided by, here I've put it as, okay, this is all a, a, okay, 2kpx the whole divided by a square will be 0. So this will be x square square. So this will be 2kpx divided by x raised to 4. This is 2kp by x cube. So E net, the net electric field is going to be equal to 2kp by x cube. E net. Alright. So now if you want to write it in terms of 1 by 4 pi, you can also write it as 1 by 4 pi epsilon naught 2p by x cube. K is 1 by 4 pi epsilon naught. Okay. So I've done the derivation here. I've also typed out the derivation for those of you who want it that way as well. Okay. So however you want it, you can look at it. Is that fine? Hi Ravinandan. Hi Toxic. I didn't forget you, Toxic. I was just not looking at the chat. I didn't want to lose the flow of the derivations. I was not looking at the chat. That's why. Okay, this is a very important derivation, students. And diagram is very important. Without diagram, you will not get marks here. All right. Yes. No. Ravi Nandan. Hi. All right. So that is how you get the electric field on axial line. So here you can see, students, the dipole and the electric field are in the same direction. Okay. How do I get that? So here you can see what is the direction of the dipole. Dipole is from negative to positive. Okay. So this is the direction of the dipole. Now look at the direction of the electric field. E2 is greater. So electric field is also along the same direction. So dipole and electric field, same direction. Okay? Yes. So that is what is here. So this is the final expression for axial and they are both in the same direction. Atharv is such a caring person. I will drink water, Atharv. I have water here, okay? Yeah. Okay. So let's move on to a question based on the same thing, okay? A short electric dipole has a dipole moment of magnitude 3 into 10 raised to minus 29 coulomb meter. The electric field due to this dipole at a point on the axial line is at a distance of 0.1 meter from its center in vacuum. Okay, blah, blah, blah. But here it's directly given that you have a dipole, okay? You have a dipole, you have a point P. You have a point P and you have to find out the electric field at that point P and it's axial. So you directly use the formula for axial. What is the formula for axial? E is equal to 2kp by x cube, which is equal to 1 by 4 pi epsilon naught kp by x cube. So what is this? 9 into 10 raised to 9 into k is how much? Sorry, k is 9 into 10 raised to 9. P is, where is it given in the question? 3, right? Okay, 2 into 3 into 10 raised to minus 29. The whole divided by x. X is how much? 0.1 meters. So this is 0.1 cube. Now if you do the math, you will get the answer. Hi Nagappa Koravar. Nagappa wants Sunita. Why are you putting Sunita's name in my class? Okay, Sunita is another student. Sunita Lokesh. Hi Sunita. So what's between Nagappa and Sunita? The next example we should use Nagappa and Sunita. Heli Nagappa. Sunita is asking. Okay. Now let's move on to, you can do the math. So what will it become? 9 into 2 into 3, it will be 54. So this will be 54 into 10 raised to 9 minus 29 divided by 0.1. When you take it up, you will get 10 raised to minus 17. Okay? Okay. Alright. Is that clear to all of you? So we've done the derivation, we've looked at a formula as well. Next, what we're going to do is we are going to find out the electric field on the equatorial line of a short dipole. Okay. So what are we going to do? We're going to do a similar thing but a different formula. So electric field at an equatorial line on a dipole. Okay. So again, figure first. Alright. Nothing. I was just looking at the chat, students. So watching it recorded, I'm really sorry. You can fast forward all this. So something really interesting happening in the chat. That's why. So we have two dipoles. This is minus q. Okay. This is plus q. This is a dipole. Okay. I said two dipoles, but two charges that make a dipole. Minus q and plus q. Now I have to find out the electric field at a point which is equatorial to the charges, which means this is my point. Okay. Axial means along the same plane, but equatorial means at a point above. Do you understand the difference? Axial is this, equatorial is at a point above. Okay. Now let this be the midpoint, and this is where? This is the distance. Okay. So the midpoint is O. Now this distance is A, this distance is also A. So the total distance is 2A. Okay. Yes. Now let's think that. Let me see if R is the alphabet used. Okay. R is the alphabet used. This is X. Alright. I want to use the same alphabets. Okay. Because in different books you will see different alphabets. So I'll use the same alphabets that I've done in my typed version. Okay. R, X, R. Okay. So the dipoles are the point P is at a distance R with respect to each of the charges. It is at a distance X with respect to the midpoint. Now what else should I do? I can mark the electric fields. So at point P, the electric field because of minus Q will be along minus Q. For plus Q, it will be against plus Q. Okay. So if this is charge 1 and this is charge 2, this is going to be E1 and this is going to be E2. Now how will the resultant be? This way. This will be E net. The resultant. Alright. Now if the dipoles make an angle theta, if this is also theta, they both make an angle of theta, then these two will also make an angle theta. Okay. These two will also make an angle theta. This is the basic diagram. Is this diagram clear to all of you? Okay, I hope this is clear to all of you. Okay, now what we will do? Let's just find out the distance first. So let's just take R. So R is the hypotenuse of the triangle. So shouldn't R be equal to side square plus side square? Since R is the hypotenuse, it should be equal to side square plus side square, R square. So R should be equal to square root of x square plus a square. Okay, I'm writing all the important parameters first. Next is the angle. So you can see that this is 1, this is 2, this is the net. Okay, so this is going to be the vertical component and this is going to be the horizontal component for this particular angle. So let me draw that here. So if this is theta, then the adjacent side is going to be cos theta. So this is going to be cos theta, and the opposite side, which means this side is going to be sin theta. So this side will also be sin theta. So if I take another angle here, this side will also be sin theta. So in this triangle, this side will be E2 sin theta and this side will be E1 cos theta. The same thing happens for both the angles. Okay, so you can see that what you can see is, that if this is a line, this is your first E, this is my second E. Since they're equal and opposite, I'll just put it as E. I don't put it as E1 and E2. Okay. So you can see this is going to be E sin theta. This is also going to be E sin theta. This is going to be E cos theta. This is also going to be E cos theta. So E sin theta and E sin theta are equal and they're opposite as well. Right? They're going to be of the same size and they're going to be opposite. So you can cancel them out. Why is my eraser not working? My cos theta and sin theta does not want to go away from the board. Eraser, please work. Okay. Okay. Wherever I don't want it, it has worked. So what was it here? R square is equal to x square plus a square. Okay. So now E sin theta and E sin theta will cancel. So the resultant will be E cos theta. Okay. Now let's write down whatever we need. Let's take green. Let's make it colorful. So E1 is what? KQ divided by the distance R square, which is equal to KQ divided by x square plus a square. And this is also equal to E2 because they're at equidistant. They're the same. Okay. E2 is also going to be equal to KQ x square plus a square. Since E1 and E2, this I will write, this is also equal to E. Okay. Now, E net, the net electric field is going to be equal to, what is it going to be equal to? This is the net electric field. These two will cancel. So the net electric field is going to be equal to E cos theta plus E cos theta. Isn't it? E cos theta plus E cos theta. So it is going to be equal to 2 E cos theta, which is going to be equal to 2 KQ x square plus a square times cos theta. Okay. Now what is cos theta? So cos theta is, if this is theta, cos theta will be, okay, let's just take this triangle. Cos theta will be adjacent side, which is Okay, sorry, we can take this triangle. This is the cos theta triangle. Okay. So if you take this triangle, cos theta will be adjacent side, which is A, divided by R. Okay. Let's just do that here. So cos theta will be A by R, which is equal to A divided by square root of x square plus A square. Okay. So I'm going to substitute the same thing here. So this is now going to be equal to 2k cube x square plus A square. Instead of cos theta, I'll write A divided by square root of x square plus A square. Now it's just simple math. Okay. What do? I will just write it as 2. I will write it inside, so I can write it as P. So this will be K times 2QA. 2QA I can write it as P. This is raised to 1. Okay, I will do all the steps. X square plus A square raised to 1. X square plus A square square root. So raised to 1 by 2. 1 by 2 plus 1 is 3 by 2. So this is going to be equal to 2QA into K, the whole divided by x square plus A square, the whole raised to 3 by 2, which is Kp divided by x square plus A square, the whole raised to 3 by 2. Okay. Now what we will do? We will do the same thing. If x is very, very, very greater than A, then this will be Kp the whole divided by x cube. X square raised to 3 by 2 is going to be x cube. So E net will be Kp divided by x cube. Okay. So students, if this diagram is clear to you, then the rest is sorted. Okay. Then you will be able to do the rest. If the diagram is clear to you. Okay. Hi Chetan. Welcome to the class. Sunita, please respond. Chetan wants to know if you ate. You have so many caring people in class. Okay, now students, I've just done the same thing here as well. Alright. So you will get, instead of k, I've just written it as 1 by 4 pi epsilon naught. Now what is the comparison? How can you compare? Electric fields of axial line and equatorial line? The only difference is that E axial is equal to 2 times E equatorial. Okay. So the axial line and the equatorial, the difference is 2. Axial is 2p by x cube. Equatorial is p by x cube. Okay. Now, what about the direction of dipole moment in electric field? So in the case of an equatorial one, so this is point P. Okay. So you can see that the electric field is along this direction, right? The electric field is along this direction. But you can see the dipoles, they're in which direction? This is negative. This is positive. So the dipole is from negative to positive. It's in this direction. Okay. Do you understand? Electric field is in this direction. How did I get it from my previous figure? See, electric fields were, this is the direction of the negative, this is the direction of positive, and the resultant is this way. So electric field is in this direction, but dipole is always from negative to positive, so it's this way. So you can see that electric field and dipole, they are opposite. But in the case of axial, they were along the same plane. In the case of equatorial, they are opposite in direction. Nagappa, I am right now from Bangalore. I am in Bangalore, but originally I am from Kerala. Okay? Yeah. Where are you from, Nagappa? Is this clear to all of you? Students? Yes? No? Not interested? Next. An electric dipole has a dipole. Okay, this is a question. Okay. An electric dipole has a dipole moment of P. The electric field at a point P on its axial line is E. What is the magnitude of electric field at a point on the equatorial line? So if it's equatorial, what should the formula be? An electric dipole moment is P. Electric field along the axial line is E. What is the moment of the equatorial? So what is the relation between E axial and equatorial? E axial is equal to 2 times E equatorial. Yeah. 2 times E equatorial. Okay. So, if E axial is, E, then E equatorial should be E by 2. Very easy. Directly you can say, isn't it? If E axial is E, E equatorial should be E by 2. Very easy. Okay. So that's about dipole. So what all did we learn of dipoles? The dipole moment of a point which is random, dipole moment on the axial, dipole moment of the equatorial. So dipole moment on axial and equatorial is very important for your PU, but on a random point, that formula is very important if you're looking into competitive exams. Okay? Yes? Is that clear to all of you? Yes? No? Okay. Next we will look at, okay? So we can look at torque. Now, torque. What is torque? So for that, let me first draw an image. I've written image, but I've not drawn the image. Where is the image? Let me draw it for you. For torque, first you consider an electric field. Okay? So you're considering an electric field E. Okay? Inside the electric field, okay, I'm going to consider a dipole. Okay? This is a dipole. So this is plus Q, this is minus Q. Okay? Plus Q and minus Q together forms my dipole. This is the center part of the dipole. This is O. Now I'll take a different color. This distance is A. This distance is also A. Okay. Now the force that acts on this dipole will be plus Q. So it will be in this direction. It is going to be equal to Q into E. But for the negative charge, it will be in the opposite direction. So this will be equal to Q into E as well. But they're going to be in two opposite directions. Since it's positive and negative, it will be in two opposite directions, QE and QE. Now, in this case, the net field or the force F net is going to be equal to 0. Why? Because it is a uniform electric field. Okay. So, in a uniform electric field, since both the forces are equal but they're in the opposite direction, the net field or the net force is going to be equal to 0. Alright. Now, the torque on an electric dipole placed in a uniform electric field when there is a small change. Okay. So, let's just consider the same figure. But here, let me assume, okay, let me write down the formula for torque. So, not for torque, for dipole moment. What is the formula for dipole moment? It is Q into 2L. Okay. Yeah. So, dipole moment is Q into 2L. And electric field is E. Okay. This much is clear. Alright. So, let's start to do it. Now, let's consider the torque acting on plus Q charges, torque 1, or the torque acting on minus Q charges, torque 2. So the total torque will be torque 1 plus torque 2. Okay. Now what is torque? Torque is basically force into the perpendicular distance. Alright. So if you're applying a force, okay, This is the thing. If you're applying a force and the perpendicular distance will give you torque. So this is basically going to be equal to force into perpendicular distance plus force into perpendicular distance. Now let's write down what the force into perpendicular distance is going to be equal to. It is going to be equal to force is charge into, so F, the general formula is charge into field. This is the general formula for charge, force. Now how will you find out the field? So what I will do is, I will take the diagram, I will make a triangle, okay. So let's assume this is a triangle, okay. Now this is the angle theta. So if this is my dipole and this is the central point, from this central point is where the dipole is going to rotate. So initially this is the electric field. So dipole has to rotate at an angle of theta. So this angle at which it rotates, this angle is called theta. And this theta is going to be equal to what? If you want to find out, okay, this is the electric field, this is the dipole, it's going to be rotating like this. So if I want to find out this rotation, which is this line, I have to look at the opposite side. So opposite side is sine theta is opposite by hypotenuse. So opposite side will be a sine theta. Okay, it's going to be a sine theta. Now same thing I will do for the other side. So here also, here this is the midpoint. It's going to rotate like this. Okay. So if this is the electric field, it's going to be rotating like this. So this is the angle theta. So this is theta. So this side will be a sine theta. This side will be a sine theta. Now I have the two sides as a sine theta. A sine theta, a sine theta. So now let me write down force into perpendicular distance. Force will be Q into E a sine theta plus Q into E a sine theta. Okay. So this is going to be equal to 2 times Q into E a sine theta. So this is going to be equal to 2QA will be P. So PE sine theta. Torque is PE sine theta. Now theta is the angle between P and E. So torque can be written as P cross E, which is the same as PE sine theta. Okay. So torque can be written as P cross E as well, which is PE sine theta. Do you understand the students? Yes, no? Okay. Ma'am, can you take class on smart board? RXBTCC, I don't have a smart board at home, okay, and I live very far away from the Vedantu studio, so that's why I'm not able to take a class on the smart board, okay. All right. Torque is equal to P cross E. Okay. Now, some of you might be wondering why. What if I write it as E cross P? Okay. What if I don't write it as P cross E? What if I write it as E cross P? What is going to happen? So let's look at that as well. Yeah, let's look at that as well. So I'll take a green color. Okay. So right now, this is how the torque is. Okay. This is the dipole. This is the electric field. So it's going to rotate and it's going to do this. Okay. So in which direction is it rotating? It's rotating clockwise. So here it's rotating this way. Here is rotating this way. It's rotating clockwise. Okay. Now if you want to take P cross E, P cross E will mean PE sine theta. So that is the only case where it's going to rotate clockwise. Okay. So if this is your dipole moment P. Okay. And then electric field is along this direction. So if this is theta, only this way it will rotate. So if it's this way, it has to be P cross E. Okay. So you shouldn't put it as E cross P. E cross P is wrong. It is P cross E. Okay, next we will look at the two conditions. So that is what I have written here as well. Now, some of you might be thinking, what is this torque? Ma'am is talking about torque for a long time. Torque is something that makes anything rotate. Okay, it's something that makes things rotate. So if this is a dipole and this has to rotate in an electric field, it has to have a torque. Okay. The expression for torque is P cross E, which is PE sine theta, which we just discussed. Now, the special cases. When is the torque maximum? Okay. So, when is the torque maximum? Let's address that. Now, if this is the electric field, okay. If this is the electric field, this is the electric field, and this is the torque. Sorry, this is the dipole. Okay. So, this is plus Q, this is minus Q. The whole, this is A, this is A. This is the center O. Now, in this case, see, this dipole is completely perpendicular to the electric field. So, the natural tendency of the dipole is to become parallel to the electric field. So, that is where it has the maximum torque. So, here, what is the angle? What is sine theta? So, torque is equal to PE sine theta. Okay. Now, sine theta, for sine theta to be maximum, it has to be plus or minus 1. Isn't it? Only then torque will be PE. So, when will sine theta be plus or minus 1? When it is 90 degree or 270 degree. So, theta should be 90 or 270. Only then sine theta will be plus or minus 1. Okay. Now, so this will be what? Torque will be PE, which is basically Q2A into E. Okay. Now, visually, I just explained it to you. If all the fields are like this, if the torque is perpendicular, if the momentum dipole is perpendicular, it won't be stable unless it aligns itself with the field. So, that is when it has to be maximum. Okay. Okay. Next is, so it is basically when dipole moment and electric field are perpendicular to each other. Next question is, when is the torque minimum? When is the torque minimum or 0? When is the torque minimum or 0? So, for the torque to be minimum, torque should be equal to 0. Okay. So, for that, theta should be either 0 or 180. Only then, sine theta will be 0. Okay. For torque to be 0, sine theta should be 0. So, the net force should be 0. Theta should be 0. And what about the net torque? The net torque should also be 0. Okay. So, what is the condition? What is the diagram? So, let's look at that. The electric field is like this. Okay. So, this is the direction of electric field. Now, the dipole, I'll draw it like this. So, the dipole is going to be like this. P. So, there's going to be QE on this direction, QE along this direction. These are the forces. Okay. So, this is minus Q. This is plus Q. And this point is P. Now, the same thing I can draw. Okay. Let me just copy this. Control C. Control V. Okay. Now, the only difference is going to be that what's happening? Yeah. Difference is going to be that. Yeah. This is going to be plus, this is going to be minus. So these are the two conditions, okay? So you have an electric field, you have a dipole which is parallel to the electric field, okay? But in one case, you can see the direction of dipole moment is it's opposite in both the cases. In the first case, direction of dipole moment is like this. In the second case, the direction of dipole moment is like this, okay? Directions of dipole moment are opposite in both the cases. Now, in this case, this system is in equilibrium, okay, or this is stable, whereas this is unstable. Now, why do I say that? In both the cases, torque is maximum, but why do I say one is stable and the other is unstable? For that, let's look at an example. So, imagine I'm going to move the torque, okay? I move the torque along this direction such that this will be my plus q, this will be my minus q, okay? So, from here, I give it a slight displacement. Okay, so this is my torque, this is my dipole. I slightly displace it like this. Okay, now what happens? It immediately comes back. Why? Because it is in it. This is where it is stable when it is parallel to the electric field. So if I make it move by a small angle, it still comes back. And it might go down, but it still comes back. So what happens? It just undergoes this motion. It goes up, comes back, goes down, comes back, because it is the most happiest when it is like this. See, it's like some people are very comfortable at home. They might step out, but they want to step in immediately. Again, they might step out, but they want to step in immediately because they are the most comfortable when they are at home. Okay, so that is why, if I just displace it with plus q, it immediately comes back. All right, so that means the net force acting on it will be 0. The net torque acting on it will also be 0. Now, if you take the same thing here, so imagine here, so this is plus q and this is minus q. So this is the unstable equilibrium. So you move it like this. It doesn't come back. It goes this way. Okay, do you understand that? I wish I could have written plus q and minus q. So this is plus q. All right, this is plus q. So I move it like this. It doesn't come back, but it does this. Okay, because it is more stable like this. So unstable, it is unstable because if you just displace it, it doesn't come back to its initial position. It takes the stable position. A stable position is a position where electric fields try to align the dipole along the direction of the electric field. It is very comfortable there. So however you displace it, comes back to the same position. The second one is unstable because if you displace it, it just goes to the stable position. Okay? Do you understand that? Yes, no? Okay? How are you, Chetan? Somebody's asking how you are. Hi, Neelam. Hi, hi, hi. Bravo, message. Okay. Okay. Nothing important, I think. So now let's look at question related to this. Is this much clear to all of you? So if it is, this is all if it's a uniform electric field, okay? So in a uniform electric field, okay, let me write that down. So in a uniform electric field, the net force is always equal to 0, okay, because it always aligns. The net torque may or may not be 0. It depends on the position of the dipole. May or may not be 0. Torque is P cross E. Okay. So torque may or may not be equal to 0. Okay. Now let's look at a quick question. What just happened here? Okay. Now let's look at a quick question. So what is a question? So let's say that there is a dipole, okay? you have to find the acceleration, the angular acceleration. Find the angular acceleration. Find the angular acceleration alpha of a dipole. Okay, find the angular acceleration alpha for dipole just at the moment the dipole is released. Okay, just at the moment the dipole is released. Some of you might be wondering, what is ma'am saying? I am telling you the question is released. So let's draw the figure. Electric field. Okay. Dipole will draw in green. So dipole is here, minus Q plus Q. Okay. Minus Q and plus Q. So this is at an angle 30 degree with respect to the field. This is O, this is A, this is A. These have masses M and M. Okay. So this much is given to you in the question. Okay. So this much is given to you in the question. So let's solve it. Let us solve it. So we all know torque is what? Torque is PE sine theta. So this is nothing else but Q 2A E sine theta. So this is Q into 2A E sine 30 degree. Okay, 30 degree is given in the figure is given in the question. Now we have to find out angular acceleration. So angular acceleration is basically, there's a formula, torque is equal to I alpha. What is I? I is the moment of inertia. I is the moment of inertia. Now how do I find moment of inertia here? So I is basically m1r1 square plus m2r2 square plus it just goes on like that. Isn't it? So here it's going to be equal to ml square plus ma square plus ma square. Why? A is the distance, m is the mass. ma square plus ma square. This is going to be equal to 2ma square. This is first PUC. Okay. Yeah. So torque will be equal to 2ma square into alpha. Now I will substitute that. So 2ma square into alpha should be equal to q2a e sine 30. 2a will cancel. So what remains? ma alpha is equal to QE sine 30 is 1 by 2. So QE by 2. So alpha will be QE divided by 2ma. Okay. So this is the acceleration immediately when the dipole is released. Okay. So as the dipole is released, as it moves, the angle keeps on changing. See, only when it does alpha is 30, the angle theta is 30, you get alpha is QE by 2ma. So the moment it is released, the acceleration is QE by 2ma. But after some time, what happens? This angle keeps on increasing. It's no longer 30, it keeps on changing. Okay, so it might decrease or increase on how the dipole moves. So it keeps on changing. So after some time, the acceleration, to find out, you need to use another step. But now, immediately when the dipole moves, the acceleration is going to be equal to QE into 2ma. Is that clear to all of you? Yes? No? Can I have some response? Hello, Kavya sis. Okay. No doubts in the chat. All right. Now let's do one more quick question and then we will wind up the class. Okay. So one more question. Let me write down the question. Question. Find the time period T of oscillation. Find the time period T of oscillation. Okay. If we displace dipole slightly from stable equilibrium position. What is the stable equilibrium position? Where the dipole is aligned in the direction of electric field, that we already learned. Okay. So if this is the electric field, okay, and it is in the stable equilibrium position, so it is like this. It has to be minus q plus q. It should be, the dipole should be in the direction of the electric field. So this is the stable position. Now what we are going to do is we are going to slightly displace it. Okay, so we'll slightly displace it. Now the dipole is here. So this is minus q, this is plus q. The dipole has slightly shifted by an angle of theta. Okay, so yeah. So what happens? Initially the dipole was in stable position. You make it move. So obviously, if a dipole moves from the stable position, it has to come back to its actual position. So this angle, this torque is what we have to find out. So we will just call it as the restoring torque. Okay. Why do we call it as the restoring torque? Because it's a restoring force. It's bringing it back to equilibrium. So restoring torque will be equal to PE sine theta. Now sine theta can approximately be equal to theta because it's very small. See, I am just showing you this big angle, but it's actually a very small angle. So I will just write it as PE theta. Okay. So sine theta is approximately equal to theta. Alright. Now, the force, the restoring force acting on a body should be proportional to minus x. How did I get that? First PU SHM. The restoring force should always be proportional to minus x. So, similar to that, if I take it similar to that, the torque should be proportional to minus theta. So, I am taking the linear and the angular. Linearly, force should be proportional to minus x. So, angularly, torque should be proportional to minus theta. So, torque will be proportional to, torque should be equal to PE is equal to minus theta. And it's not wrong as well because I'm taking it in this direction and coming back in the opposite direction. So it should be minus theta. Now what is torque? In the last question we already did it. I alpha. Okay. So I alpha is going to be equal to PE into minus theta. Now what is normal acceleration? According to SHF, normal acceleration is minus omega square x. Okay, normally acceleration is minus omega square x. Now, angular acceleration will be what? Minus omega square theta. That's the only difference. Linearly acceleration is minus omega square x. Angularly acceleration is minus omega square theta. So now those who are wondering what all is ma'am writing, you have to go revise your first PU portions. Okay? Yeah. So this will be I minus omega square theta is equal to PE minus theta. So theta will cancel. So minus minus can also cancel. So I omega square is equal to PE. Now from this, omega is square root of PE by I. Now the question is to find out time period, right? So time period generally is 2 pi by omega. So this is going to be equal to 2 pi square root of I by PE. Okay. So this is the time period for a dipole that is in stable position. If it's moved by a small angle, it comes back, and the coming back is by a time period of 2 pi I by PE. So what actually happens is it will come back. It might go down, it will again come back. So what actually happens is it will oscillate. It will oscillate with a small frequency. Okay, so that is what is going to happen. It will oscillate with a small frequency. Okay, so now students, in this chapter, in this section, let's just quickly recall on what all we've learned. Okay, so what all did we learn? We learned about a uniform electric field. What did we learn about a uniform electric field? That in a uniform electric field, if you have a dipole, the net force is always zero. What about the net torque? The net torque is going to be equal to P cross E, which is going to be equal to PE sine theta, and it may or may not be zero, depending on the angle. May or may not be zero. Okay, so torque is zero, theta. Okay, so when torque is zero, if theta is equal to 0, or theta could also be 180. So when theta is equal to 0, it is stable. So when theta is equal to 180, it is unstable. Students, are you hearing a noise? I'm really sorry. I'll just finish it very quickly. For a non-uniform electric field, what happens? The net field, the net force, it may or may not be zero. But the net torque, this also may or may not be zero. Okay. So this is the general formula for a uniform electric field. It may or may not be zero. Okay. So there is some disturbance here, students. So I will wind up with that. So I'll see you in another class with the rest of the chapter. I'm really sorry for this noise. There's something happening outside. Okay.